Hello everyone. In this video I'd like to show you how to plot transcritical bifurcation using MATCONT. So the previous video I've shown saddle point bifurcation, and on that video I've shown how to open MATCONT and all the stuff. But in this video I'm not going to do all those things. So first we have to load the system, name, coordinate, parameters, and time. Then we have to load the system. The equation is x dot equals to rx minus x square, and first three things are in symbolically, and last two are numerically. So hit OK, and then go to type initial point. To start with things, you have to give an initial point. Excuse me. So first, for t equals to 0, give a random initial condition. For x 0.1, and for r you can take anything. Say I'm taking +2. Hit enter. Now change your change interval in your integrator window. Make it 100. You can make it 1000. It will take a bit more time. Now you have to open two windows. First is numeric window, and the second one is 2D plot. So in the 2D plot, first we have to find the fixed point. To find the fixed point, we have to integrate the system with respect to time. So it's been set. The x-axis is time, and the y-axis we are having x. And we'll change the plotting region, say from -20 to +20. Any value you can choose. -30 to +30. And please don't close the starter and integrator window while doing the process. Now we are all set to find the fixed point, so go to the MATCONT window and compute, hit forward, and look at the numeric window. We are having x equals to 1.999, and you can go on with compute x10, but I am not doing this because we are having a fixed point. You will see a very less change in x if we extend the integration, and that is been confirmed by the graph. You can see it's a straight line, it's not varying with time. So, and it's been saved in carb PO1. Now we will go to select, go to initial point, and P01 last point, that is the fixed point. We'll select the fixed point, and as you can see in the starter window, we have started with t equals to 0, x equals to some random condition, but it is being changed to the fixed point value. And now we have to set this fixed point as our equilibrium point. And you can see a change in the starter window. That is radio button came just beside R. Just hit that radio button, and now, as you know, our bifurcation diagram is between our coordinate and between our parameter. So we have to change the plotting variable on axis. So put parameter on axis, and coordinate is fine, and plotting region is also fine. Just for getting the new bifurcation diagram, we have to set one more thing. Just come back to numeric window layout, hit eigenvalue, and hit OK. So we'll check the eigenvalues to get the proper knowledge, the diagram, that the branches we are getting are stable or not. So we are done, and just hit compute and forward. We just look the eigenvalues and the graph. So the upper part is stable, as the real part of the eigenvalue is positive. So it will go on increasing like that. Now compute backward. See, it's still negative, and here we are finding a branch point, and the eigenvalue became 0. And so this is the point where stability is being exchanged. So we'll resume the calculation, and we'll see the eigenvalue will change to a real part of the eigenvalue will be changed to positive values. That means, as you can see, it's positive, so that means the branch you are getting right now is unstable. You can check furthermore that on that branch, is there any more branch point or limit point or anything like that. You can go on by after this you can go on by compute extend, but we are not doing this. So we have our lower part of the branch point in EP2, as you can see in the MATCONT window curve, and the upper point of the upper half of the branch point we have in EP1. So to have the full bifurcation diagram, again, we have a bifurcation in x equals to 0, and that is along y equals to 0 axis. So to get that diagram, the thing is, MATLAB will start up with the initial condition x equals to 0, and before doing that, the first one that what we got is t equals to 0. We started with t equals to 0 and x equals to a random initial condition. Now we'll start with t equals to 0 and x equals to 0, and r value, anything you can take, positive, negative, it won't matter that much. So but when we'll again do for x equals to 0, t equals to 0, the EPP1 and EPP2 will be updated. So we have to change the name of EPP1 and EPP2, first EPP1 and EPP2. To do that, come to your MATLAB window, and you have to go to the EPP1 and EPP2 file. The path is cd space, um, type capital S and then tab. You will find systems. Now your the file name you have given. So probably I have given the file name as Transcritical. Okay, yes. Transcritical bifurcation. Yes. Then you have to go to diagram. Type two or three words and then type tab. It will come. So please look at the current directory in the left side. We will right now you can see epp1 and epp2.mat. So I am changing the name of epp1 and epp2. Say we are making it t1 and t2. Okay, so again you have to come back to the MATCONT window. So the command is this cd, and as you can see, hit 1 2 3 times, and now check the current directory. We're in MATCONT. So we'll again go back to MATCONT, and we'll go to type initial point. Now as you see, for the previous case, it's 100 and the fixed point. What we'll do, we'll put t equals to 0, x equals to 0, and r value whatever it is, positive, negative. Okay, you can change this to negative, like -2. You can do it, no problem. Hit enter. Okay, then everything is fine. Now come to layout, variable and axis. First we have to do the time integration to find the fixed point. Okay, so now compute forward. See, we have a fixed point at x equals to 0 now, and it's been saved in PO2. So again go to select initial point, find PO2, and PO2 last point is this. Select the point and see, starter window, t equals to 100 and x equals to 0. 0 is your fixed point. So make this fixed point your equilibrium point, and check this radio button in starter window, and just just come back to layout and variable on axis, change it to parameter, hit OK. So we are done. Now compute forward. See, you have a branch point, and on that branch point it's been resumed, so resume it. See, that branch you are getting on the right side, it's having a positive value, so it's unstable, and so, and if you compute it backward, we're having negative values. Like in some cases you can go compute extend, you can check without with extending it. So I'm stopping the extension. Okay. So we are done with these diagrams, and now we have to get the total view of the bifurcation diagram. To have that, we have to again go to that path I have shown you, CD. Just put upper arrow, and you will be that you will have that path. And first, load your T1 with tab T1.mat. So in T1.mat we have to check first. Before that, come to your workspace. In your workspace you can find a matrix called F and a matrix called X. F matrix dimension, please look, it's 1 into 300, and X matrix dimension is 2 into 300. So F matrix where your eigenvalues is been stored, and X matrix where your parameter value is shown, and parameter is in the second row. Please remember, parameter is in the second row, and we are having one row for F. So we have to check from which value to which value we are having, um, which actually will plot our parameter versus our eigenvalues. So I am writing a command. Look, column equals to 1, I put f f f colon means we are checking for every, we are having one row, so you can write 1 there, and we are checking first column, and we are checking with second row. As I shown you, for X matrix the second row is we are having is our parameter, and we are checking first element. So for F, number one row, number one column, 1 1, and X2 1, we are checking the value. Okay, see, so first value is for F, it's having a negative value, so that means the system is stable. So we have to find from where the stability is being exchanged to positive values. It's been changed to positive values. First one, F value. F value is our eigenvalue. So see, it's 10 for column, say, and look, we are having 300 columns. So I am in 10, so I am checking for 100, say. So it's minus, it is go on increasing, it is going on increasing. So yes, so we are plotting, so this part is totally stable, so we are plotting this part. Just this command you have to hit, and you can see your plot by this is your total stable branch. Now now just write hold on to hold the graph, and then again you have to do for first you have to load your other file. Load T2, tab T2. Now again we have to go on checking all. From column 1 we are checking. So see, first we are having a minus value, that means stable. So go for column 10, still it's minus, sorry, it's 19, say 30, still it minus, make it 50. Now it's plus. See, the eigenvalue for column 30 is having a is less than 0, and in column 50 it is positive. So we have to check in which column the value is being changed. So to find that, we will come to 40 first. 40 still positive, so 35 check, it's minus, so it's both 37 is positive, so 36 is our point, I guess so. Yes, 36 is 0. So what we will do, up to 36 is the stable branch, so we'll first plot up to 36 like this. Second x parameter value from 1 to 36 we will plot 1 to 36, and also x value 1 to 36. You can see the plot. Probably you are thinking it's not much changed, but yes, it is changed a bit. Okay, then this is our stable branch, and for the unstable branch what we have to do, we have to put everything else 36 to end. End means 300 here, so you can write 300 also, no problem. See, it's been again changed. So we have this y equals to mx branch. Now to have that y equals to 0 branch, we have to load pp1. Now here also we have to check again for which column value it's been changed or it's not been changed. See, it's minus, eigenvalues are minus, we are having no problem, it's still minus. Check for 100, it's positive, so somewhere it's been changed, so we have to check it where. Check it 20, it's still minus. Check 25, minus. Check for 30, it's positive, so somewhere between 25 and 30. Check for 27, it's 0, so 27 is our point. So again plot from 1 to 27. Here also 1 from 27. x1 is our x1 is our eigenvalues and x2 is our parameter value, remember. To 27, so you can check your diagram. See, we are having a small branch, and now again you have to plot the rest. 27 to end. This is our unstable branch. As you can see, I have checked for 30 and the eigenvalue is positive, so it will be on your right side. So let's do it. So check the plot. See, we are having a right side. This branch is in right side. Now we are having one file left. Load ep, load ep2. You can check this thing from 1 to 300, but it will always be minus because this is the left half, so it will go on increasing. So I'm showing you how. So see, it's always negative. Eigenvalue is always negative, always less than 0, so this branch is stable. So what we have to do, we just have to plot again, plot all those values, just take them out. Plot all those values and you will have your final bifurcation diagram. Yes, this is your final bifurcation diagram. This is bit extended. Probably you are thinking why this is bit extended, because in the backward integration I have extended the calculations, so it's bit extended. So you don't have to worry about that. So go to this point and it will come like this. So this is your stable branch. bold it. You can do so many tricks over here. You can make it look like your your bifurcation diagram, what you do in your class, in your copy. This is unstable branch, so we are putting this line, change the color. So this is your final bifurcation diagram. It is called transcritical bifurcation. Thank you.